Hello, I'm Zach, and I'm going to be completing the second problem from the array problem set from Cal Academy. Alright, so what does the problem ask us for? It asks us to find the magic index in a sorted array of distinct integers. A magic index is such that the array at the given index is equal to the given index. Basically, the element in this array is equal to its index. That's a magic index. Okay, cool. So let's look at our input and output. We're given this array of ints. We have -2, -1, 0, 3, and 5. Our output should be 3. Why 3? Well, if we go across and look at the indices, 0, -2 is not 0, -1 is not 1, 0 is not 2, but 3 is 3. So this guy is our magic index, right there. That's our guy. So we can approach this problem in a couple different ways. One of them is an ON, time complexity solution, wherein we could simply, iterate through each and every one of these numbers, and we could simply ask, all right, is the number I'm currently on, does it look like my index? We could simply just do that. But, that may take a long time, because if you're given a data set that's like, I don't know, millions of integers, that'll take a long time. And we don't have a lot of time for programmers, right? So we need to go fast. So there is an O log n solution that we could use for this. We can divide and conquer using O log n. That's much, much faster than n. And what it will do is it will be breaking down, it'll be looking at one half of the array and then just recurse into that array and then break it into subarrays. So that is what we want to do. That is a quicker solution. So let's get our pens out here. So let's think about how this is going to work. So since it's sorted, we want to do a binary search. Binary search is good for sorted arrays. So how binary search works, binary search, it is going to take in an array, and it's also going to, while it's going through this array, it's going to have a low and a high, or a left and a right, to refer to our index position. So starting out for binary search, always have your low start at 0, and then we'll have our high start at the very last index of the array. And how we are going to use these guys is we're going to add these guys together and divide them by 2. Binary, right? To give us our midpoint. So that's what the next step we want in this logic. We want to take our low, we want to add it to our high, we want to divide it by 2. And this will give us our midpoint, which we will use as a way to check where we're at in the array, if the index is the element, or if it's greater than the element, or if it's less than the element. And depending on those givens, conditions, we'll do something. So, for example, if the mid is truly equal to the element we're on, we're simply going to just return that mid. It's much simpler to do that. That's an ideal. It's an ideal world. That's what we want. We want to just return the mid if we find it. But what if we don't? Okay. What do we do? What do we do if we don't find it? Okay. We want to say else if we don't find the mid, and maybe the mid is maybe the mid is greater than. Maybe the mid is greater than the current element. If the mid's greater than the current element, that signifies to us that it's more likely that on the right side or the higher end of our array will live a number that matches the index. So like, for instance, like if this was, I don't know, if we could take this example and rewrite it a little bit, like if our midpoint was something extreme, like negative 400, and we had negative 500 and negative 600, immediately this would tell me, okay, my mid is greater than negative 400, and there's only 4 elements. Oh my God, I need to move to the right, because there's no possible way I'm going to have a negative index. That just doesn't happen. It doesn't exist. So we have to move to the right. And that's what we're going to tell our low to do. We want to redefine the range. That's the thing about binary search. We're redefining the range of our search. In this case, we want to redefine our range to be this upper half. So how do we do that? Well, we'll just tell our low to be equal to where the mid currently is, which is like, for our case, it's 2 starting out. This is the mid starting out. It's 2. So we want this lower end to basically be pushed up to 3. So that way, when we add them up together right here to generate our mid, it's a new mid, and that new mid will point up here to this 3. So that's what we're going to do. So now, in our example, if our mid was 2 and or if our low was 0 starting out, and we now just made our low be where the mid is plus 1, we're at 3. If we do 3 plus 4 equals 7, and we cut that in half, that's going to give us roughly 3.5. But in JavaScript, we'll do some fancy math flooring and make that a nice whole number, which will give us this 3 up here, which is actually what we're looking for. We're looking for that element 3. So we will recurse again, and we will ask the same question. All right, now we have a new mid. It's 3 now. Is 3 equal to the element it's on? Oh yeah, it does. Because the new mid is no longer this guy. Let me just erase this here too. It's no longer 2 anymore, it's 3. So yes. We have a match. So bam, we return the mid right there. And this is how we would find 3. But if, let's say that the mid starting out wasn't, like the mid, the number, the element that we're on is actually much bigger than the mid. Let's say it was 1,000, or not 1,000. Let's not get crazy now. Oh yeah, we could say like 1,000, and say it's 1,000, and then back over yonder, towards 0 and 1, we have 1, and we have -2. And over here we have like a really large number, 3,000, another really large number, 5,000, okay? So if we are on the other case where we're not asking is the mid greater than the current element, but what if the current element is greater than the mid? Well, if we look at this, that's 1,000. If you're the midpoint right now, right, which is 2, and you're on the element that's 1,000, there's no way that you're going to like anytime soon be getting to the index towards the right, towards the upper half. So logically, we should reset our high to a range that is closer to where the left is, or where the mid is, rather. So for our else statement here, which is basically saying else the mid is less than current element, we want to reset our high to be equal to where the mid is, minus 1. So then our range now, all right, is going to be the low plus the high. So the low automatically is 0, and then the high is now the high is going to be the high will be 1. So we're going to add 0 plus 1. We're going to divide that, and that's going to give us, or excuse me, I think I did my math wrong a little bit here. So if before our low, I assumed that our low was going to be 0. It's not always going to be 0, it's going to be changing, right? So we changed it before. We made the mid plus 1, so that was 3 well, no, it's 0 right now. Sorry, I'm getting a little tripped up. I'm just going to take a second to reevaluate my thoughts here so I don't gibberish for too long. So if this is our mid starting out, which is 2, and then we see that this number is greater than 2, it's going to be, the high is going to be moved to 1. So the high will be equal to 1. And the low, if this was our given example, is 0. So if we add them together, we have 1. 1 divided by 2, that's what, 0.5. So that would give us, if we rounded down, that would give us, it would in fact give us 0. So the mid would be 0. So the mid would be 0. And now that the mid is 0, we ask the same questions. All right, is the mid the element? No, it's not. Is the index greater than the current element? It is. Okay, so then we're going to add 1 to it, move it over here, and then we're going to re-add our mid. We're going to reassign our mid again and do our low plus our high divided by 2. Our low would now be 1 plus the 1 gives us 2 divided by 2 gives us 1. So we're here now. And we ask the question, is our mid equal to the element? It is. We did it, gang. It's 1. So we get 1 for this example. And this would give us back the output of 1. Cool. Perfect. So to keep this loop going, a few times I've mentioned we're going to be recursing. So so far we haven't seen any recursing happening, so I'm going to delve into that a little bit right now. So when I say recursing, I don't actually want to make a function that calls itself. Instead, I want to do something simple, like what binary search usually, how it's written is with a simple while loop. So I want to do a while loop, and I want to have some kind of exit condition for this while loop. And I basically want to say, as long as the low is less than or equal to the high, keep on going, keep on finding. Because I know by the time they overlap, I've gone too far. So I have to exit. I've looked at everything, there's nothing there. So in that case, if there's nothing there, if I didn't return inside of the loop, then oh boy, we're gonna do something really fun here. We're gonna return -1. So we've looked through it, and there's nothing in there. We're just gonna return -1. It doesn't exist. So let me just mute my computer before the timer alarms me. Okay, so let me write out the pseudo solution to this problem. Let me get my handy dandy markers here. Okay, so this is going to be called, let's see, say const. We'll say find my magic index. And this is going to be accepting an array. And it's a sorted array, not just any array. And we're going to do some stuff now. So, first thing we're going to do is we're going to assign our low. We're going to say it's 0. We're going to assign our high. We're going to say it's the array dot length -1. We can just create the variable mid here, doesn't matter. If we create it here or inside of our while loop, and now we're going to get into the while loop. And we're going to say, while our low is less than or equal to our high, and remember, if all else fails, return negative, looks like a 2, oh my god. We're going to return 1. A 1. Okay, so let's do some math. Okay, we're going to generate our midpoint, our mid index. And we're going to use JavaScript's math.floor because why not? We can't do it any other way. All right, low plus high. Inside, we're going to pass in low plus high divided by 2. So that way, if we get a float, we're going to floor it down, and it's going to turn it into a 2. Perfect. Then once we do that, we're going to say if the mid is equal to the element where mid is in the array, then we are just going to simply return mid. Okay? Let me try to... Oy. Getting real slim right now. It's like a Slim Fast commercial. Okay, so now else if the midpoint is greater than the element at the midpoint, okay, so then we are in trouble, right? So we need to go to the right. So we're gonna say left equal to where the midpoint is plus 1. Else, if all else fails, we are going to, or rather else meaning the mid is less than, we're going to make the right, equal to the mid minus 1, because as I said, if we had a gigantic number here, we don't bother searching in the range up there, so we move back down here. So mid minus 1. Perfect. Now if that doesn't work, well, I hate to break it to you, boss, but you're going to have to return -1. Now, let me see if I have my curly braces in order. All right, that is to this one, and that is to this one. And yep, okay. And I think this will do it for now. Until next time. Thank you.